are very special in terms of classical particle systems. Very special in the sense that that for such systems you don't have actually a point-like particle, but instead in particle you have some special extent, and so you'll have some kind of excluded volume that will need to be taken into account in the field equation that will define interactions between the particles, and that will lead to various very particular effects and difficulties. And so, yeah, in a nutshell, we'll need to couple somehow mean field limits together with kind of homogenization limits for field equations defining interaction. All right, so when I'm talking about suspension, so this is of course what I have in mind. So you just imagine you have some fluid, maybe in some tank, and then you put a lot of particles, of rigid particles in your fluid. So the particles just move around, they just follow the fluid flow. And then of course each particle, so they are rigid particles, so they somehow they hinder a little bit the fluid flow. So they generate some fluid disturbance, and that's how they are interacting together, right? They just interact via the fluid flow that they are performing. Right, so this is the kind of system I would like to consider, and of course you all know just by experience that whenever you have a particle suspension, on our scale you must expect very complicated and Newtonian effects. I mean, whenever you are in your kitchen, you prepare some sauce. I mean, you see that. I mean, the usual industrial example is just ketchup. When you put just ketchup on a plate, I mean, it's not flowing. I mean, it's very viscous. It's probably a quasi-solid. I don't know. But then whenever you shake a ketchup bottle, you know that you will fluidify the ketchup and it will start flowing easily. So that's a typical example of shear thinning. It's a non-linear effect, which is really typical for. And you also have like memory effects for ketchup because it will be fluidified for a couple of seconds and before becoming a quasi-solid gas. And so this is the kind of thing I would like to understand and describe. So kind of deriving such kind of Newtonian effects really from this kind of model of particles in fluid. Right. So let me just start by by describing the particle system and writing down equations for the system, so we see the difficulty. So there will be a couple of parameters. So you want to intend to consider large-scale limits. So we'll have a very large number of rigid particles. So n will be the number, and then you have very small particles of size, let's say epsilon. So that could be like the diameter. And so there is another parameter which is the volume fraction. I will call it lambda, which is just the number times the volume of particles. So n epsilon d. So at the moment, let's think that the volume fraction is somehow fixed. Very quickly, we'll take it quite small. All right, and just for simplicity, I will neglect, as usual, actually, the inertia of the fluid. So I will not consider Navier-Stokes, but just Stokes equation for the fluid flow. And then I will also actually neglect inertia of the particle. So I will not write down Newton's equation for the particle, but just the balance of forces. I mean, as usual, if you don't neglect inertia, if you consider full Newton's equation, actually the mean field limit result will be as difficult as proving somehow, as deriving somehow the Vlasov-Poisson. So, I mean, they have essentially no result in that direction. All right, so then those are the equation I'd like to consider. So first I need to describe my particle. So for some reason, that will become very clear very quickly. So I don't want to consider just spherical particles. I also want to consider particles that may have some orientation. So let's say some ellipsoids of revolution or whatever that are just characterized by the center and then their orientation. So Rn's will just be orientation that are just unit vectors for particles. And so let me just describe the equation. So first you have the Stokes equation for the fluid flow. So U will be the fluid velocity. So this is just Stokes equation, steady Stokes equation. When it's Laplacian velocity equal pressure equals some, and then you put some internal force, I call it H. Then divergence vanishes. But of course, you just have the Stokes equation in the fluid domain, so outside of the particle. So you have a Stokes equation in a perforated domain. And then you need to add some bounding conditions. And what is kind of natural is to say that you have like no slip boundary conditions at the boundary of the particles. So meaning that at the boundary of the particles, the fluid velocity should just be like the velocity of the particle. Because particles are rigid, it means that you should just have something, a rigid rigid free flow at the boundary of the particle. So here I'm writing here, so that's the symmetric gradient of the velocity that should vanish at the boundary, and okay, let's also extend it inside the particle. We just mean that at the boundary or inside the particles, the velocity field would just be some rigid motion, so you have some translational motion and also some rotational motion, like that. And then there is, Newton's equation of motion. Here I just want to write down a balance of forces, which will just take form. So let me not describe that in detail, but that's the kind of form it will take. So it looks like some kind of flux condition in terms of the sigma, which is this usual Cauchy stress tensor. All right, and so here I take into account both some internal force, but also maybe some sedimentation force that will actually not play a very important role here. And I also have maybe a balance of torques that's written in that way. So a priori it might seem like you have too many boundary conditions. You have like a Dirichlet boundary condition, and then also those flux conditions. So the point is that this is not a full Dirichlet boundary condition, because I'm just saying that at the boundary the velocity should be equal to some rigid motion, but v and w's are not fixed. Right? They're also part of the unknowns. So and in fact those vn's and wn, you can view them just as Lagrange multipliers for those flux conditions. All right. So now this system actually is well posed. So you should just think that it's a Stokes equation in a perforated domain with rigid boundary conditions. And so it's well posed. So given the positions of the particles, you can just solve this steady Stokes equation. You get a velocity, and you get also velocities then of the different particles, the translational and rotational velocity. Right. So that's yes.
What is h in the first equation?
H is some internal force that you put. So some force. So there are two forces. There is this H, internal force, and then some sedimentation. So you should think that this integral, this flux here is the force that is exerted by the fluid on the particle, and then you add gravity, that is E. Just right, some constant. All right, and then so this gives you when you solve that, this gives you velocities of the different particles, and then you can just write down the particle dynamics. You just update the position and orientations just according to velocities you have. Right? And okay, so very recently it was proven that in fact the system is globally well posed in time in generality, provided you just like some smoothness of the particles. So that's some result of Mathieu-Guéret and Labisse-Sabach. All right, so this is a system I'd like to consider, and you immediately see, some kind of particularities of this dynamics, which is that you really see that velocity fields are not just given as some explicit sum of pairwise forces from other particles. So the velocity I just obtained by solving this Stokes PD which is a PD in a perforated domain. So where you see that actually all the other particles are appearing as boundary conditions. So you see that it's really like multi-body interactions between the particles. So this is the first particularity. And so you have like multi-body interactions between the particles, which are also not explicit, which is kind of different from kind of usual canonical setting you usually consider. And then there will be a very quickly various other difficulties. So in particular, the interaction will be singular, and you know that it's like a usual big difficulty when you prove mean field limits. So in fact, when you have two particles that you try to push together, the pressure will somehow blow up in the middle, and that's why that's why actually the dynamics is well posed. You never have finite collisions. And so it's a bit unclear what I mean by singularity, as we will see, is essentially similar to like Coulomb type singularities. Somehow at short distances in a certain sense. So it doesn't really mean anything because you don't have pairwise interaction, and also some part of the interaction will be even more singular, as we will see in some sense later. And then you also have the dual difficulty that not only it's singular, but also it's long range, which will actually be quite problematic for some stuff. So it will decay quite slowly on large distances. All right, so now what do we actually expect for such a system? Well, so first of all, there is this equation that defines the fluid velocities, which is this perforated Stokes equation, and so that's a Stokes equation with steady Stokes equation with rigid inclusions, and so rigid inclusion just behave in this steady Stokes equation as some kind of heterogeneities, right? And so when you look on large scales, you expect to have some averaging that will be going on, and you expect on large scales that you should that this Stokes equation should be replaced by some effective one, and so some effective one in terms of some kind of effective viscosity. Which depends non-linearly on the whole set of particles in a certain way that will depend on the whole microstructure of particles. And now that's the thing. So in particular, if you think of such a picture where particles go, completely disordered, you should have certain effective viscosity that should be completely different from this kind of situation where all the particles would be somehow aligned. But this is, of course, this microstructure is, of course, not fixed because they also follow the fluid flow and they can adapt in time. And this is exactly this coupling with the dynamics of the microstructure is what will create a non-Newtonian effect. So if you just think about ketchup, when you have ketchup at rest on your plate, you have this kind of picture where you have like entangled polymers, and of course it doesn't flow nicely, but whenever you shake the bottle, somehow you align all the polymers, the particles, and you fluidify in that direction the ketchup. All right, so the main difficulty in the end will be to try keeping track in some sense of this microscopic dynamics in the effective description of the system. All right, so that will be the goal for today. And so what I should start with certainly is to describe a little bit this homogenization process, just to, this will not be the main topic, so I will be quite quick on that, but just to really define the notion of effective viscosity from which we will start, and that we will then try to couple to the dynamics so that we really see what will be going on. Okay, so let me just start with that kind of just to define the main object. Right, so this is the kind of statement you might expect, right? So hey, because it's just about averaging, for simplicity, I will just assume that we're in a spatially homogeneous setting. So the set of particles, just take it as being some epsilon rescaling of some, let's say, some random ensemble that is spatially homogeneous. And so what you expect is when you have this kind of perforated Stokes problem with rigid boundary conditions, on large scale, I was saying you would expect that the solution will be just approximated by the solution of some effective problem like this. So it is just a Stokes problem where now you have an effective constant, B bar, that we call the effective viscosity. And in the right-hand side, it is just the weak limit of forces. Right? You had some internal force in the fluid domain. So in the limit, it should just be 1 minus the volume fraction of the particles times h, and then also plus maybe some contribution from sedimentation forces. And of course, because particles are rigid, you should view them as having like infinite viscosity. So when you're averaging, you expect the effective viscosity to be larger than just the viscosity of the plane fluid, which should just be 1. Right? So. So now I just need actually to define this effective viscosity, and for that I need to do a very brief incursion into like homogenization. And so here's kind of the general picture. So I just need to write down the relevant object that would be a correct equation. So the general picture is like that. So you have some equation in an heterogeneous medium. So here you have like rigid inclusions, and so a steady Stokes equation. So the solution, the fluid flow will somehow oscillate at the scale epsilon of heterogeneity. This is the blue graph. But then when epsilon is very small, you expect that everything will somehow compensate and you will have some kind of effective profile that will be smooth on a scale like this U bar. Right, and now you'd like to describe this U bar. In fact, to understand U bar, you first need to try understanding a little bit the behavior of small-scale oscillations. So if you want to do that, so let's try to zoom in the graph of this. So when you zoom in, well, because U bar, this effective profile is nice and smooth, it will just locally look like something linear. And U bar is a solution of Stokes, so when you zoom in, you should have something linear like Ex, where E is trace-free, so that Ex would be a solution of the free Stokes, steady Stokes problem. But now when you zoom in, U epsilon is oscillating at small scale, so when you zoom in, you should correspond to order 1 oscillations around this kind of Euclidean coordinate. That's how the free Stokes equation. And now those oscillations should exactly be made to be adapted to the microstructure, right? So then this is a natural question: what is actually the canonical oscillation you should put around linear coordinates, around Euclidean coordinates, to make it adapted to the presence of heterogeneities? And this is exactly given by the notion of corrector. So you just want to correct Euclidean coordinates by adding what we call a corrector psi, so that this is now a solution of the Stokes equation with those rigid boundary conditions inside the particle. So just of the corresponding heterogeneous problem. Right? So the corrector is really just like about correcting Euclidean coordinates to transform them into like intrinsic coordinates adapted to the microstructure. All right, so then this is what we call the correct equation. And just a comment, so because it's about microstructure, you are zooming in, so now it's a problem in whole space, in infinite volume RD, and you have data on the inclusion, which is especially homogeneous, so you're in a spatially homogeneous setting. So of course, making sense of such equations is always a bit tricky. But the only thing which is really important is just to think that this corrector, it should correct Euclidean coordinates, so it should be sublinear, right? So that's infinity. All right, and then it's the usual problem in homogenization to try making sense of such problems. I will not spend time on that. But so now the idea is that you understand formally small-scale oscillation. So the true solution should just be like this effective profile. And if you want to be precise in H1, you'd need to add those kind of oscillation exactly given by the corrector. So this is some kind of a Taylor expansion in intrinsic coordinate, if you like. And now, actually, when you have this, it's very easy to see what U bar should actually be, this effective profile should actually be. Let's just think about the energy. If you think about the energy of the perforated Stokes problem, you can just replace this two-scale expansion, and it will immediately yield an energy, quadratic energy for the effective profile, with now some constant that will be this effective viscosity, as we will call it, that is exactly given, and you understand it naturally, by somehow the infinite volume energy of the corrector. So this is just like the ensemble average of the energy density of intrinsic coordinates. Right? So this is the correct notion of effective viscosity. Let me now just state this kind of theorem, which is now very well understood, that indeed solution will converge to some effective profile, where effective viscosity is just like this expectation of the energy density of intrinsic coordinates that are given by this kind of corrector. All right. So, okay, so I just needed to introduce this kind of corrector problem because we appear very often. Right, so now what we would like to do is somehow to couple this kind of homogenization with the dynamic of the microstructure, right? So, and the main point is that there are somehow two big obstructions. So first, because it's about microstructure. Now the microstructure dynamics should be a dynamics for an infinite number of particles, infinite volume, so that's always kind of very delicate to actually define in this setting. We really don't know how to do. And also because you are zooming in, it becomes a fast dynamics, and which will also be very problematic. So the first thing before actually coupling to the dynamics is to actually trying to really understand a little bit better how the effective viscosity depends on the microstructure. So here it just depends, we are the correctors on the microstructure, but we'd like to simplify that a little bit, and so it's kind of natural to consider a dilute regime, because if you are kind of dilute, when particles don't see each other that much, their interaction should be kind of small, and you can imagine to expand the effective viscosity just in terms of, in a way that just involves some reduced information on microstructure, the full microstructure directly, which is too complicated. And this type of expansion of effective behavior is something which is very usual, that was done a lot in 19th century by physicists. And here for the effective viscosity, it was first really considered by Einstein in his PhD thesis. So the idea is that if you look at this effective viscosity, well, to leading order, when you don't have many particles, it should just be like identical, like the plane fluid viscosity. Then you should have corrections, and so then you should have corrections, right? And so what is this about? So this effective viscosity is this energy of the corrector. And you're in a dilute regime, so you want to say that essentially particles just feel isolated, they don't see each other that much, so you want to replace this energy of the corrector by somehow averaging, by just summing the contribution from single particle energies, right? And this is the kind of thing that now you can expect, that you will get an effect because it's about averaging over different particles. So it's an effect that will be proportional to the volume fraction, and that will just be given by averaging the single particle corrector energy. So here this psi 0 will be the corresponding corrector for just one particle. So one particle, you solve the corresponding corrector problem. So now it's something actually decaying, because you just have one particle where you need to correct linear Euclidean coordinates. And then you are just averaging over, well, it depends on the orientation, you're just averaging over the law of orientations. This is this F1, the law of the one particle density of orientation. So you see, to first order, you have completely simplified the dependence on microstructure. You just depend on the density of the single particle density of orientation. I mean, really nothing surprising. And if you consider 3D spherical particles, as Einstein was actually doing, then you can compute that explicitly, and you just have the universal factor 5/2, which is Einstein's effective viscosity formula. So this has been really studied a lot recently. So we also have like a very quick proof, optimal proof with Antoine Gloria, which is really based on this kind of variational idea that you want to approximate the whole corrector energy by just a superposition of single particle energies in a way. But that's not the topic for today. Today I want to actually to have a full description of the effective viscosity. So I want to understand all corrections and try to couple that with the dynamics as much as we can. So I want to also to understand higher order. It's kind of natural. I mean, when you have two particles, of course, two particle solution. It's not just about the Stokes problem of the corrector equation. It's not just about superposing single particle solutions. Of course, they interact in a certain way, and so you expect that the next order should be given by summing now two particle effects and three particle effects, and so on. So, of course, there is a natural cluster expansion we would like to write down, and actually justifying it is kind of tricky, and that's the first result I would like to advertise a little bit. So first, I need just to tell you what I mean here in this case by cluster expansion, and before stating that result. All right, so more generally, so we have when you have a set function that depends on let's say a set of indices. So I want to call it cluster expansion. So this kind of expansion around the empty set. So I just want to say that first you approximate by f just of the empty set, then you start taking into account the contribution of singletons. So you sum over n of indices, f of n minus f of the empty set. So this is kind of a first order finite difference. I will call it delta n. Then the next thing should be taken into account the contribution of pairs of particles that are not already understood by a singleton. So this is this kind of second order difference operator. So I call it delta nm of etc. Right?
I just have a question. So, I mean, when you look at times in which it's also, I mean, the scattering between the particles is mediated by the fluid, but it's also, they can also scatter as hard spheres, or I mean...
They will never collide in finite time.
Okay.
That's the question you were asking.
Yeah,
so the thing is that when the thing is that it's a bit strange, but when you have Stokes, when you have particles in the Stokes field, so even if you have one particle which is falling under gravity to a plane, it's actually known that it's some result of also Mathieu Hilleray and David Gerava that actually the particle will never touch so in fact when you have two particles that become very close, they become somewhat sticky. They will not touch, but they will. Right. Okay. So if you try to push them together, the pressure will be blowing up, and that's why they will not touch in finite time. They will somehow form maybe a cluster and move together.
Mm-hmm. Okay.
So here we are just fixing like so we are just looking at this kind of steady state part. So we are fixing the position of the particle. We are just looking at the problem that defines the fluid velocity and the velocity of the particles. And then we would like to couple it to the dynamics, but there will be no collision. All right, and so this kind of cluster expansion, now you can do it. I mean, for our effective viscosity, which is now depending on the whole set of on the whole microstructures, the whole set of particles. So this corrector depending on the whole index set, that's a natural number. So now psi s will be corrector just associated to particles indexed by s. Right? All right, so you can do a similar kind of cluster expansion. So to leading order, you just have psi of the empty set. If you don't have particle where you need to correct, of course the corrector is 0, so you just have like e squared. Then the first correction should be you just sum over particles, and you have this first order difference of the corrector energy, then the sum over pairs, etc. And this is really like decomposing somehow multi-body interactions between the particles. I mean, this is really just checking how when you have two particles, it's not just about superposing the single particle behaviors, but you have some correction, second order term.
And I mean, that's an expansion in lambda.
So it should be, but okay. So but that's a great question. So we saw the first term should be of order lambda, and then I mean actually in physics paper usually you see that the next term should be lambda squared. In fact, I mean this cannot be true in general. I mean I think it's even my next slide. Oh yes, it's actually the next slide. So the scaling of the terms is not that simple, and I mean it will be important. We will try to couple to the dynamics. So if you look at the first term, so what are the scaling of different terms? So if you look just at the first term, it's a sum of the particles and you take expectation. So So it's a point process. So you can just write as an integral with respect to the one particle density of the point process, which is constant because you are spatially homogeneous. So this is just the intensity of the point process, or which is essentially the volume fraction of the point process, lambda. So you see the first term is certainly of order lambda formally. Now when you look at the second term, of course it's the expectation of sum over pairs. So now you can write as an integral with respect to the two particle density. And of course the two particle density in general is not tensorized, right? So there is no reason why this should be the square of lambda, right? So in general the second term should just be of the order of F2, which can be much larger, of course, than lambda squared, right? So of course, I mean, in many settings, if you have like Poisson process, it should be a lambda squared. If you have like, if particles are uniformly far from one another, you can also show that it's like the square of the size of B1. But in general, I mean, just think of a process where you would have like clusters of particles all the time. Of course, there is no reason why B2 should be smaller than B1. B2, I mean, B1 is about saying that particles are essentially isolated. If you have cluster of particles that are not isolated, it's not a good approximation. Right? So this ancient formula is certainly only correct provided that you have some condition on the scarcity of clusters, too many clusters. And we'll come back to that when we talk about that. Right. And then, okay, so what are actually the difficulties if you try to establish such kind of a cluster expansion? So, I mean, there are two difficulties. First, a priori, it's an infinite series. This is actually not so much of a big deal, but there is another issue, which is that each of those terms, which define the cluster terms, they're also infinite series. So you sum over particles, sum over pairs of particles, all infinite series, and those terms are actually not converging. So, and this will be because of the long-range character of interaction between the particle, which is hidden in the Stokes equation. So more precisely, I mean, this is what happens. So if you look at what happens if you add a particle at a certain space, at a certain place. Well, at the boundary of the particle, at the position of the particle, you will feel somehow the flow disturbance which is created by all other particles. And so at the boundary of the new particle, you will get some kind of stress difference. When you compare what happens if you have or not this particle, so we'll have some kind of stress difference, and this will generate a dipole force that will be felt everywhere. So if you look at the difference of what happens if you add a particle at a certain point, it will just behave like because you look at a gradient, it will be, and it's a dipole force, it will be the second gradient essentially of a Stokes slide. So it will just decay like borderline. It will be like a minus d of the distance to the new particle you have added. Right? So now if you look at those different terms, if you just look at what they mean, so this first order difference of this corrector energy, we see that then it also just decays borderline with respect to the distance, and similarly for the next term, then it's borderline in two directions. Right? So those guys are certainly not summable, so you see that all cluster terms are just divergent. Right? So just to make sense of those terms is a priori not easy. Okay, so you might think that, okay, it's just borderline, so it should not be such a big deal, maybe, like Caylor-Rand-Simon operators are not summable, but still you can make sense of sums. But in fact, it's quite tricky, so I mean, there is a famous story of three papers of Burgers in the 40s, where in each one he actually proposed some way to renormalize, and each time he obtained a different numerical answer. So I mean, actually getting the correct renormalization is not so clear. And so to first order, actually, it's not very difficult. It's like there is one gradient that you integrate and that becomes zero. But starting at the second order, and then you just get essentially Einstein's formula. But when we started with the second term, actually, it's much more tricky. The second term was understood formally by Batchelor in the 70s. In some physics paper, but actually understanding renormalization to higher orders was not understood. It's more tricky. I mean, this kind of trick by Batchelor is really just not working, and you need something else. And so for that, I mean, that's something I wanted to briefly explain. Briefly explain the idea. So in fact, there is some way to renormalize to all orders, and the idea is to think a bit about to try using the method of reflection. So which is somehow a method that gives you some formal expansion of multi-particle solution in terms of single particle operators. So I mean, the idea is that if you have like two particles, right? Those are two particles, and you try measuring the flow disturbance at a certain point in space, let's say at the origin. So of course you can say that first you will consider just the free flow without the two particles. Then you want to consider the effect of the particles. And again, at the boundary of each particle, if you now consider them, you will have some stress difference that will generate some some dipole force that you can measure at the origin. So this is the first part of the diagram. Those contributions just coming from the flow disturbance coming from one particle. But now this flow disturbance can also be felt by the second particle, right? And then this will create a new stress difference that will now again generate a dipole force that will again be felt at the origin. So that's the second diagram, and you can continue. I mean, the first one will also, the second one will also be felt by the first one, and so on. You have all those kind of diagrams. So the thing is that those kind of extensions are not converging in general. So we don't really want to use them. But the idea is that each of those edges, each of those arrows correspond to some dipole force. So they correspond to some borderline decay. And so whenever you have more and more arrows, more and more edges, you have more and more decay in those variables. So actually all the higher order diagrams, essentially, you can just think of them as having enough decay to make sense of everything. So problematic parts are really just coming for the first time. So when you look at finding all the difference of correctors, like those deltas, I mean, you have cancellation, natural cancellation, you get that kind of thing. And now this is the kind of expansion you want to formally put inside the cluster formulas and try to see what's happening. Maybe you get some cancellation. Indeed, that's exactly what happened. So the first term are just some kind of explicit combinations of Stokes sleds, essentially. So they are quite explicit, and you can, at the level, you can actually get a lot of cancellations. And this is typically what happens if you look, for example, at the second order term. It's very easy to check that you will just get reduced to some integrable kernels plus some borderline kernel that will remain. But now, because of cancellation, you will be able to integrate this borderline part not just with the two-particle density, but you will replace it by two-particle correlation function. So you can somehow subtract the value at infinity of the density thanks to those precise cancellations. And now whenever you have some decay of correlation, then of course this integral will be perfectly integrable, it will make sense, and you are happy. Right, so of course, to make that a bit more precise, you need, I mean, you don't want to use really the method of reflection, you want somehow to truncate, just to single out the first explicit term that are just borderline, and just to say that all other terms have enough decay. So you can do that in kind of a systematic way. And then there is some kind of systematic procedure just to capture at that level, to capture what kind of diagrams will give rise to cancellation, what kind of cancellation, and you just get in the end, at all orders, sum of perfectly integrable expressions. Right. So that's the first result I wanted to advertise. So that if you look at this effective viscosity, you can indeed expand it. Now, probably not as a Power series in lambda, it's more complicated result, but you can expand it to arbitrary order. You can make sense of this kind of cluster extension, where the error, so if you truncate all the k, the error, so up to logarithm, essentially will be like the size of fk plus 1, so the k plus 1 particle density. And if you look at each of the terms, so the terms number j will just be a sum of some integrals involving a correlation function up to order j. So you see that you really reduce the dependence on the microstructure. You just depend, so at order j, you just depend on correlation function for up to j particles. And up to logarithm again, which are in general optimal, it doesn't really matter. So the size of bj will just be like the size of fj. So you have the same kind of observation that we had for second order, that indeed, if you, I mean, this expansion will be accurate in the sense that the error will be much smaller than the other terms, provided that fk plus 1 is smaller than fk, which is just saying that you don't have like, that you have some scarcity of large clusters, which is kind of naturally what you want, and which is somehow expressed. So that's some result with Antoine Gloria that you obtained last year to
So just a naive question. So in your expansion, when you have two particle dots connected by two lines, that's better, right? I mean, because then you get more decay.
Yes, you have twice. Yeah, exactly.
So the problem is when you have just one.
Yeah, exactly. So exactly. So, but when you have a lot of particles, you need to be a bit careful because, for example, this one you have a double edge here, but you don't.
But that is bad. Okay.
Yeah, exactly. So you still need to have something quite explicit to have some cancellation there.
But then, and then you deal with the problematic terms by exploiting cancellation. I mean, somehow.
Yeah. So here, essentially, here you have a double edge. I mean, that is somehow summarizing a whole expansion that you don't want to write down. So this is not so much explicit, but this one is explicit. This first thing will be somehow explicit, and it will allow to see some cancellations. And so, for instance, when you will then integrate, you will be able to, thanks to cancellation, to just remove something and to get just some direct links come from correlation functions. So you will have some correlation function coupling some other variables, and so you will get enough decay. Right. So okay. So now we have this better understanding of the effective viscosity, this kind of dilute regime, and so we can now try to couple that with the dynamics. So let's go back to the dynamics. You have this again, this perforated Stokes problem that defines the fluid velocity and the velocities of the particles, and now you want to update position orientations with that and to track the dynamics. Okay, so let's just recap what you did. So first of all, I mean, this Stokes equation on large scale, it would behave like the solution of some effective Stokes problem with effective viscosity that you now expand so that perturbatively it only involves like the one particle density and correlation functions. Okay, so let's no longer assume, let's say that things are uniform in space. So F is with the one particle density of positions and orientation. That doesn't really matter. And so now this is what we'd like to couple to the dynamics. So what do you actually expect on for the dynamics? So in the end, what you expect is maybe something like this. So you'll have some kind of homogenized equation for the macroscopic velocity, which is just some Stokes equation where you have this kind of expansion in terms of correlation functions between the particles equal to all the forces, and then you need to write down some dynamics for F, for the one particle density, and for correlation. So for the one particle density, well, I mean, this is one particle density, so you expect to have some mean field kind of equation. So well, one particle density, you should just say that it is just pushed. I mean, one particle will just follow the fluid flow, so it should just be transported by U bar, the macroscopic fluid flow, and then it should also turn around, well, depending on the fluid deformation in a certain way. So I don't, well, this omega explicitly doesn't really matter, but it should just turn in a certain way depending on the local fluid deformation, local macroscopic fluid deformation. But then the problem is what happens for particle correlation. The point is that this is not like usual correlation, macroscopic correlation functions. This is really microscopic correlation functions that are really describing the behavior of several particles at small scale. So for example, H2 will certainly not be small in general. So like the microscopic two-particle density will typically not be tensorized because locally, I mean, the particle will not be independent at all. So those are microscopic quantities, and again, trying to describe the dynamics is quite tricky because a priori it should again be some kind of fast dynamics because it's for microscopic information. So this is really again a critical issue. We don't really know how to even to describe such kind of thing. It should be a fast dynamics. You don't really have relaxation. So we don't really know what it means. So there is a natural first simplification that we will do from now on, which is to try just to forget about cluster effects. And in fact, even if you forget about cluster effects, you will still get some non-trivial, non-Newtonian effects, as you will see. So what do I mean by neglecting cluster effects? Well, it will mean exactly neglecting B2 and all higher order terms, which come from more than just one particle behavior. But now we saw that B2 in principle can be as large as B1. So whenever you have closed particles, whenever you have closed particles, they will behave like a super particle with a different shape, and of course this will modify the Einstein correction term in the effective viscosity. So the first thing, if you want to neglect a cluster effects, you need to assume that you have some separation of size of the different terms in this expansion. So for that, for instance, you can just you don't have a lot of choice, but you need really to assume that particles are well separated. So let's say that the minimal distance is like the typical distance between particle n minus 1 over d.
Sorry, Mitya.
Yes.
So now you're looking at the dynamics.
Yes.
So this assumption is a positive time or a
No.
time?
So this is, let's say, yeah, okay. So this is, let's say, initially, but then you can propagate it.
And you can propagate.
Yeah, but you don't propagate it forever because if you wait a lot, of course, there should be clusters forming. But you can actually, so if you are very dilute, you can propagate it quite far in time. So in fact, it's even long time if you are dilute enough. Yeah. So suppose you just impose that initially, and then you can propagate it. And so if that's true, then of course we saw that if you're well separated, the second term should be like lambda squared. essentially. So now, if you need a smaller and smaller contribution, you can just focus on the lambda contribution and forget about higher order contributions. This is not something.
And so the behavior of your interaction that you show in the beginning, the sign matters. So you have
What do you mean by this?
so it has to be some kind of repulsive interaction.
Yeah. So I said that when you have those particles in the fluid, they are somehow repelling each other. They will not. They will not collide in final. So
because of the pressure or because of
the pressure somehow. If you try to push two particles together, the fluid needs to escape, and so the pressure should be going up. Okay.
So then neglecting them from B2 to 1, this is the Einstein's approximation.
Yeah, exactly. So you just focus on Einstein's contribution, you forget about high order effects, which are involving a correlation that you cannot really follow in the dynamics. All right. So then if you remove all that from those equations, you just keep Einstein's correction, you forget higher order terms, and then you don't have any correlation function, you just have this mean field equation. And then this is what we call the Doi model, or maybe Doi type models, variation of Doi models. And this is still actually non-trivial because, as you see, so F includes like the orientations of the particle. You see that particles the orientation is just evolving depending on fluid deformation, and then it arrives in Einstein's correction terms. So it gives some nonlinear contribution, and so what you see here exactly in this Doi model is exactly the non-Newtonian effects that are coming from collective orientations of the particles. Right? This is just about collective way, the collective orientation of the particle, which is captured here by mean field, and how it appears in the field. Right. So in other words, we start from the way to compute a velocity is via this kind of perforated Stokes equation, and this led to some kind of non-trivial homogenization to occur, and in this kind of a dilute mean field regime, you see that it means that you will still get some kind of nonlinear effect coming from there, where you have some kind of non-trivial effective viscosity that really depends on some kind of microscopic information. So this is what we call multiscale models, because you have like a macroscopic fluid equation, which is coupled to some kind of kinetic equation for some microscopic information that have just like the orientation. All right. So now just a comment about so before stating the result, just a comment about let's say the proof of this kind of Doi model. So of course first, you need to you want to prove some mean field limit results. So first of all, you need to describe velocities. And so again, velocities are given by solving some equation, which is non-explicit. But now you're in a dilute regime. So again, you can use exactly this kind of cluster expansion that we just described. So to lead in order the velocity of a particle, first you just feel what the fluid flow generated by the forcing, by the internal force, and then you have corrections of order volume fraction, which is just coming from somehow interaction. So this kind of fluid flow generated by the internal force creates some stress difference. The way the stress difference is felt really depends on the orientation of the particle with respect to the orientation of the forcing. This is somehow those terms, and then those create some dipole force, which is felt by each of the particles. So you have gradient of a Stokes light, and then you have higher order terms. And then for rotational velocities, this is essentially just an additional gradient that you need to take. And so you immediately see, the next difficulty, which is that those interactions are certainly singular in this sense. So now you see that in position. So if you look at velocities, interactions between particles are via this gradient of Stokes light. So it's now singular, like a power 1 minus dimension at short distances. And in orientation, you have one more gradient, so it's even a little worse. And actually, if you look at the term of order lambda squared in the remainder here, it will also involve more singular, even more singular kernels. All right, so let's start by looking at what you can do in position. Because this is somehow tricky. You have a Coulomb-like singularity. So you could think that, we just have some first order dynamics. You have some Coulomb interaction. So now we know how to prove mean field limits for Coulomb interaction for first order dynamics. But the only proof is via those kind of modulated energy methods. And I mean, and here we don't have like a nice energy structure that you could use. I mean, you even have like remainders that are more complicated. So this is really something we don't really know how to do. But then there is something that helps, which is that you have a small parameter lambda. Right? And so even if proving mean field for a Coulomb interaction is highly tricky, you know that whenever you have a little bit less singular interactions, like sub-Coulomb kind of behavior, then actually proving mean field is much easier. And you have this kind of result, all these Oren and Jabin using infinite Wasserstein distance to actually prove mean field limit result, which is some kind of buckling argument. I mean, there are lots of variations on that proof, but essentially you just try to say that whenever you know that you are quite close to the mean field limit in some strong distance, like the infinite Wasserstein distance, this gives you also some kind of local control, for instance, on the minimum distance between particles, and then this is something you can use to actually improve on the distance to the mean field, right? So you have some kind of buckling argument you can do. All right, and so the thing is that this only works for sub-Coulomb interaction, but because you have a very small factor in front of the interaction, perturbatively you can still make it work, and you can still prove homogenization, mean field limit result there. But now what happens in orientation? Because in orientation it's even more singular. A priori it's a power minus d of the distance. And this is actually just too singular for a mean field limit result to hold. Actually, this is very comparable to what happens. I mean, this is an old remark by Ulschlager. We just noticed that whenever you have like interacting particle system where you have a pairwise interaction that is essentially critical, so you have like a power minus dimension. So here I'm just like regularizing a little bit, but let's just think about a critical power minus d. Then of course the mean field limit result makes no sense because you can integrate x minus d is not integrable locally. And so in fact what you can just notice is that whenever you look at the time derivative of the empirical measure, in the limit it can just not be any function of the limit of the empirical measure. So in fact it just means that because it's somehow critical, you are not averaging at all, and in fact the limit should depend on the geometry locally. And this is very meaningful because we saw that some corrections should involve B2, etc. That should involve a little bit of geometry. So this is just saying the same problem in a slightly different way. That you have two. I mean, you have just no mean field because you have two singular interactions. Okay. All right. So this is probably bad news because you cannot have a mean field limit result in orientation. But in fact, this is not such a big deal. In fact, you can still prove this result, which is that all your particle system is very close to what is given by the Doi model. But you just need to be careful with the accuracy. So you get indeed accuracy lambda squared essentially in velocities. You get also lambda squared in position. So mu is like the empirical measure just in position. So also lambda squared accuracy. But now if you look at the full empirical measure also in orientation, you can only have accuracy lambda. But I mean there is in fact no contradiction here. So if you look at the Doi model, you see that the density in orientation appears only in the Einstein terms, which is a factor lambda in the first equation. And so if you have accuracy lambda for f, you get accuracy lambda squared for the velocity. So this is perfectly, I mean, there is no, I mean, all this is kind of coherent. Right, and so to have that, I mean, the assumption is just that you are in a kind of a very dilute regime. You need a little bit more than just that lambda is small. You have some like log smallness. Then you have this very critical initial well separation of the particle that is then propagated in kind of quite long times. And then also you have like some well preparedness assumption, which is not really important. All right, so I just like to really emphasize this kind of double limitation we have in this result. So first, there is really this well separation assumption for the particles, which is really critical because whenever you start having clusters, which should, by the way, happen on very long times, the coefficient B2, which is the next correction to Einstein's term, should also become of order lambda and should completely change the dynamics. So, right, so this is somehow really optimal. You cannot do without that. Whenever some clusters start forming, you really change completely the dynamics. And then there is this kind of limitation in the accuracy you can reach, lambda squared in position, just lambda in orientation. And for that, again, so the reason was that beyond that, the geometry should enter into play. So either you view it by saying that, well, the next correction to Einstein should depend on microscopic correlations, or alternatively, that just you have two singular interactions, that you just don't have mean field limit, and then you don't really know how actually to describe that kind of make sort of corrections. There's also no equation proposed by physicists, to my knowledge, beyond that.
So, but instead in this regime, the mean field picture works. I mean,
yes, exactly. But those are two limitations, and you can just not go beyond that in mean field. Right. So I mean, Amina Sherbet just had one work where she was assuming that particles, that you had some cluster of particles, and she was assuming that they were somehow stable, which, by the way, you cannot prove, to my knowledge. And then, of course, B2. I mean, she doesn't write it that way, but somehow you have a new correction to Einstein's formula, which is coming from right. So let me essentially stop here. I just want maybe to go very quickly to the last part, which was one thing that essentially. So here we have this DOI model, which is this kind of multi-scale model. You couple this effective macroscopic fluid equation with some kind of kinetic equation. So I mean, heuristically, it's certainly a non-linear equation. So you certainly should see some non-Newtonian behaviors, but of course you don't see them so explicitly. But then, I mean, you can consider some kind of hydrodynamic limit where you would consider fast relaxation in orientations. So let's say for Brownian suspensions, I mean, we are currently working on also mean field for Brownian suspensions, so with Raphael Winter and Richard Hofer. And so in that kind of regime where you have a strong relaxation in orientations, of course you expect that immediately the density in orientation will adapt to the local fluid deformation. And you can expect to have some non-linear fluid equation in the limit. And in fact, this is something you can do, and you get exactly what is known as a higher order or the ordered fluid equation, which are just some kind of a nonlinear modification of Stokes equation, which are then exactly predicting some very precise non-Newtonian features. Like you can, if you go to third order, you really see that you have strain, that you have shear thinning. Already to second order, you see that you have strain thickening behaviors. You have like normal, non-zero normal stresses and other kind of properties that you can then really somehow derive directly from particle system. If you put everything together. Right. So let me stop here.
Thanks a lot for the very interesting talk. Other questions?
Yeah, so apparently this cluster expansion is a very important thing due to the collective behavior of the particles. So I have a general question about the cluster expansion. So the set function is modeling somehow the interaction between those particles, am I right? So I don't remember the slide, the most general expansion of this one here.
Yeah, so I was just saying, so here somehow the effective viscosity depends on the whole an infinite set of particles, right? So you can view that as a set function. So I'm just saying that, well, cluster expansion, I mean, it's something very natural to do. It's a general kind of combinatorial thing you can do whenever you have a set function. You can somehow make I mean, this is some kind of Taylor expansion, if you like. I mean, you can view that as some kind of discrete Taylor expansion for set functions that you just reproduce here.
And there are no further assumptions on the set function.
No, that's always true. Yes, you can just sum, and I mean this is a finite sum. If you have a finite index set, of course you can just sum up to when you sum over the whole set, and it's an equality. I mean everything just cancels. You're just adding and subtracting. Yeah.
Okay, and are there like any probabilistic methods to look at the cluster, for example? In d dimension, what is the probability that the cluster of size k might form? Or
you mean in the dynamics?
Yeah.
It can form in the dynamics. Yeah. So I don't know. I feel that whenever you have, if you're on the torus or in the bounded domain, you have many particles. I feel that whenever you wait long enough, there will be clusters forming. Okay. And the thing is that whenever you have two particles quite close, so it's true that they are somehow repelling each other. But whenever they are quite close, in fact, they are somehow sticky, and they will somehow they should somehow stay together. So in fact, this kind of this repulsion, this Coulomb repulsion, is only true in some kind of mesoscopic scale. But whenever the particles are close enough, in fact, they are somehow sticky, and they will tend to stay together.
Okay. Yeah.
So I guess that whenever you wait a little bit, there will be some cluster forming, and they will stay. Maybe you will have more cluster forming, and I don't think it's really a probabilistic result. I think it's like, I mean, even
it's just.
Oh, you can ask the question of scarcity of that. I guess they should really form if you wait long enough. Of course, if you are very dilute, particles don't interact. I mean, don't see each other that much, and then it should be very. You should wait a very long time.
Thank you.
So in your renormalization argument, I mean, I didn't quite understand. I mean, at some point, is there a resummation involved that defines some sort of effective interaction between the particles?
So somehow it's a trivial renormalization in the sense that you just have the only difficulty is just to catch I mean, physicists call it still a renormalization, but the only difficulty is really to catch cancellation.
Okay.
But once you catch cancellation properly, then essentially just if you have some decay of correlations, it's enough to make sense of everything. So there is no, if you like, there is a resummation involved when you don't really use the full method of reflex and you resum the rest. But this is, I mean, this is probably not what you think about. But I mean, this part essentially there is no resummation, and you don't also need to subtract anything to your model. I mean, this is just intrinsic somehow. Just about catching cancellations.
So the cancellation comes from the fact that your interaction is this dipole type interaction that comes
Exactly.
So when you integrate
that in fact, exactly, that the most singular part in the interaction is just given by one dipole, which is explicit, where you can just, I mean, you can see how variables depend on one another and you can catch everything.
Thanks.
Yes. In a dilute mean field, yes. Yeah, so I mean, there are two. I mean, there are several parameters, right? So essentially, yeah. So I don't know exactly what mean field means in the end, but so I mean, you have a lot of particles, so the n tends to infinity, and I mean, you're in. I mean, having a mean field, I mean, being able to write a mean field approximation just means that you can somehow average over all the forces coming from different particles. This, in principle, as we show, is not true. In the dilute regime, when lambda is small enough, then in fact you have some mean field regime. You can somehow average over the particles. So when you just look at how particles are interacting in this kind of lambda expansion, probably here, right? So actually, higher order terms are too singular to have any kind of mean field averaging that can be going on. But now for the first term at order lambda, this is just 1 over n and something you can somehow average. So there is some continued limit to that something. So that's why it's like dilute mean field. You just have a mean field approximation in a kind of suitable dilute regime.
Thanks. Okay. If there are no other questions.